Okay, so today we have the first lecture, and for this semester, I will just live stream this lecture. So you can always, anytime, visit my YouTube channel to um, see our previous lectures. So this is the first time, and yes, this is lecture one. So, technology, computer aided design. So let's go to next one. Before starting our technical session, so I just wanted to welcome you, all of you. So the title is Computational Microelectronics. In Korean, that is called as 계산전자공학, and code number is EC7114. So you know, 71 means that this is at the end of our lecture curriculum. So this is initially for graduate students, but it is welcome to have undergraduate students. And as you know, we have no experiment. However, you have to have many homework exercises so by yourself. And my name is Sungmin Hong, so I'm affiliated to the School of ECS. Okay, so let's go to available resources. So presentation materials will be distributed to our GitHub repository, specially made for our course. So why don't you just visit the Git? Okay, so then look look and oh, so this is my ID and CM Computational Microelectronics 2023 full semester. Then you can find the one, which is a repository, and when you visit there, right now we have only one PDF file for our today's lecture. So but anyway, later on we will have tons of PDF files for our every lecture. So when you click it, then you can see it directly, or you can download it. So the way I do right now is I just downloaded my file from GitHub repository and sharing it with you in this Microsoft Edge program. So also there are some other old archived repositories. So if you change the year to different ones, like 2000 something or 2000, yes, then you can find many repositories. Every year we have slightly different curriculums, so that is not perfectly matched to your proposal or your semester, but I hope that anyhow you can find some valuable information from those repositories. And oh, here I have a typo, sorry, so this is E. Homework submission. So previously I used our repository, GitHub repository for homework submission even. However, I found it is not that much comfortable, convenient, and in this case, in this semester, we will exclusively use this LMS system. So when I ask you to submit a homework, then please submit your homework to this LMS system. Have you already logged in your LMS system for this course? Some of you have done, and some of you not, but well, I think that its usually is not that difficult, so you can easily submit your first homework. So actually today we have the first homework just to show you how can we do the homework submission. So let's just go to the end of our lecture. And of course we have a YouTube channel. So YouTube channel we have many recorded lectures, so previous lectures like 2022 or 20 something. So this is an old course developed by myself, so you can find all related resources from this YouTube channel. So if you are interested, in your choice. So, and evaluation means that here you have attendance 10%. Of course, if you don't attend more than 2/3 of entire semester, you fail. That is regulation by our institute. So, in addition to that, I have 10% weighting factors for attendance. But I hope that everybody will come to this lecture room uh, quite regularly. And here we have homework 40%, so we have many homework submissions, and final presentation is 50%. So in this case, we have no mid-term examination and no final examination. All of them are just gone, and more or less your final evaluation will be based on this final presentation, and prepare and submit your own presentation. And what is the topic of your your presentation, that will be decided later after our course develop considerably. And I want to say that it will be your presentation will be uploaded in my YouTube channel. So if you cannot accept this condition, please drop this course. Okay. So I wanted to also say that the ratio between these 10%, 40%, 50%, these weighting factors are slightly modified from our original syllabus. However, more or less um, this or these weighting factors will be obeyed in our semester. Okay. So, and what else? Okay, so I think that that's all for our just admin stuffs. So do you have any question to me? 한글로 질문하셔도 됩니다. 네. 네. Okay, so if you don't have any question, then please let's go to our first lecture. Our first lecture is devoted to the introduction of technology computer-aided design. So, although our course name is computational microelectronics, but this is another name for our course, technology computer-aided design. So, I will explain what is this terminology represent and what is the importance of this research field, and some related stuff will be briefly introduced. Okay, so if you have any question, then please let me know. And let's go to this slide. So in the left figure, this figure shows a NAND gate. So here you have logical A and logical B, and here Q is the output of your logical operation. For example, if you have 0 and 0, logical 0 or logical false, then what will happen in this case? You will have logical true or value close to 1. Okay, so are you with me? And if you have any values like 1, 0, or other configuration 0, 1, or even both of them are 1, in these cases your Q value will be just 0. This NAND is not of AND. So you have an AND gate, and its output is once again inverted by this bubble here. So that's the reason why that is called as NAND. And NAND is a universal logic gate. So in principle, if you have tons of NAND gates in your system, then you can build any kind of a logical system. So that is a universal gate. Yes, so that is the one we wanted to have. So we have tons of it. And for example, sometimes you may have heard about something like this FPGA. So this is the system to build certain logical system in-field. In-field means that not fabricated in the factory, but in the field, in your research lab or some research field, you can fully change your system into certain logical functionality. So FPGA is actually made of C of NAND gate. Okay, so that is quite practical, and we are using this kind of thing. But think about this one. Is this physical reality? Uh, so of course, what is the physical reality? It really depends on everybody. So you may have this kind of thing. Other one has a different idea. But in my opinion, at least in this sense, in this logical symbol, then it is far from the physical reality and is much more abstract. So what is the logical one and what is logical zero? That is in our brain. And more physically, we can say that this logical one in this system is a voltage close to certain predefined value of a VDD. Also, this logical value 0 is a voltage whose value is quite close to the value 0, so ground. So, for example, nowadays our VDD value is more or less 0.7 volt, and if you have voltage like 0.65 volt, then maybe you can regard that voltage as logical true or logical 1. And if you have 1 millivolt in your system, then maybe you can regard it as a logical 0 or logical false. So how can we realize such kind of thing in our system? So this central figure shows one example. So typically seen by electrical engineers. So in this case, they wanted to make this kind of circuit schematic to realize the left figure's logical function. Here we have voltage A, voltage B, and voltage A and voltage B, and these are different semiconductor devices. So so what are they? So I will explain it later. But anyway, in this case, we have different 4 devices, and they react to differently this gate voltage applied to its terminal. For example, for these guys, if A or B is close to the VDD, then they become highly conductive. And when A or B is close to 0, then they become highly resistive. So following this kind of rule, so we can realize that when we have 1 and 1, for example, let's think about this 0 and 0 case. 0 and 0 case means that here we have voltage close to 0, close to 0, of course, voltage close to 0, and voltage close to 0. Then what will happen? For this device, since applied voltage is close to 0, then this one becomes highly resistive. Also, at the same time, this lower transistor, lower semiconductor device becomes also highly resistive. So now, when you consider this part called output and ground, the electrical path from this output to ground becomes highly resistive. It means that actually this output is isolated from our ground, so close to value 0. On the other hand, however, if we are looking at these devices, then this device behave completely differently. When we have 0 volt to these terminals, then it becomes highly conductive, and also it becomes highly conductive. So in this sense, from our output node to our VDD value, we have two highly conducting paths. Then what will happen? Since they are highly conductive, the voltage VDD is just copied to our output. So simply speaking, when we apply voltage close to 0 to terminal A and terminal B, then our output voltage will become VDD, and that is regarded as, once again, logical value 1. And we are now just demonstrating that when we have 0, 0 configuration for our A and B parameters, then we will have logical 1 as a output value. So I think that most of you can easily understand this kind of thing. And let's go to the rightmost one. Rightmost one also shows another representation for two input NAND gate. So this is called as a layout, and this layout is typically adopted by circuit designers. So although we can understand its operational principle using this kind of circuit schematic, if we really wanted to design and fabricate this kind of thing, so really into the silicon, then we need a further step. This is the one we take. This is a layout. Circuit designers usually draw those kind of rectangles into certain two-dimensional plane and submit it to the manufacturer. Then, following the given rule, design rule, and they means that the guys in fab fabricated this kind of um, logical operation. Okay, so this is a layout. But up to now, I have discussed about many different ways to represent same function, same logical function. So you can find that the left one is quite abstract and clean. And if we go to right one, it becomes more complicated and more physical details are hidden. But in my opinion, in this course, we are not looking at our devices or our object in research, not in this way. The way we are looking at our two input NAND gate is like this. This is, in my opinion, this is a physical reality of our two input NAND, at least in this course. Of course, if you are coming from more fundamental department, then you may interested with more detailed analysis in these interfaces or some other quantities. But as an electrical engineer, I think that this is kind of the bottom level we can expect for this electrical system. So that here we have VDD and VSS, that is corresponding to ground, and VDD 0.7 volt, and AB and Z, they are related with two input parameters and one single output parameters. Then in order to realize this kind of function, actually we have to build this kind of system. Of course, how thick is it? Its thickness is around several micrometer scale, and the most important part is maybe this one. This is related with some scale of a few 10 nanometer or a few 100 nanometer scale. So anyway, we have to make many different inner structures to realize a really simple logical function NAND. So in order to realize a simple NAND, then actually we have to make this one. Oh, so this right figure just shows the enlarged version of our NAND, and I think that maybe we are looking at around here. here we have some structures, gray structure, two gray sticks here, and these two gray sticks are also shown here and here. This one is intentionally eliminated to improve the visibility. And you know that this stick, vertical stick, is called as a fin. So structure called a fin, and this structure is important for this device. Usually this transistor is called as, maybe you have heard about it, so FinFET. So anyway, although we simply call it as a FinFET, but inside it we have of course a fin, and fin is surrounded by insulated layer, and it is covered by also gate material, metal, and also we have interconnect. So we have so many different materials and inner structures to realize our logical functionality. So simply speaking, it is a complicated structure and complicated system, and just by looking at it, you cannot understand its operation. Or understanding is okay. However, if I ask you how much the current will conduct if we apply the VDD to our gate and drain, can you estimate it? So it's not possible because there are too many parameters and too many details in it. So I think that this is already far beyond the human's capability to predict its electrical performance. So what should we do? So of course we have to use computer simulation. I think that if this device isn't just a commodity, then everybody will not be concerned about this one. However, as all of you understand, nowadays semiconductor device technology is not just a matter of economics. It becomes more and more difficult and important to develop next generation device technology. It becomes even more like geopolitical issues in these days. So point is, semiconductor device technology is always pressured to improve its performance every given period. For example, you are now looking at certain slide taken from TSMC's last year IDM presentation. So this is just 8 months ago or 9 months ago. So here we have their baseline. This N5 means that there are 5 nanometer node, and they wanted to build now 3 nanometer node. Although 5 or 3 is not really related with the physical dimension, but anyway, let's just follow their convention. So this is their baseline technology, and they say that, oh, we have now introduced 3 different options. One option, another option, or another option. So now it's your choice to take any of them, then improve your chip performance. So okay, but anyway, please have a look at the direction of your arrows. How many arrows do you have? You have 3 arrows. One arrows more close to the vertical direction, and another one is more close to the horizontal direction. But anyway, all of them just showing this kind of direction. What is it? Please interpret it. This direction shows that your area is reduced, and at the same time your speed is increased. So this is something like this. So for example, if we are talking about a car, then it means that we are always asked to make a smaller engine size, however faster car speed. So that is required by our industry, so semiconductor device industry. Okay, so then how many years are allowed for a company to achieve this goal? So not 10 years. This is just orders of 2 or 3 years. So within this given time, every company in this competition should achieve the next generation technology development. So in this sense, trial and error approach is not acceptable. So if your company fail to develop the next generation technology, then what will happen? Then actually this is the failure of an entire company. So because in this industry, winner takes all, so we are hungry for the most advanced technology. So simply speaking, we need a guide to the better technology development. So you can easily understand this one. So in this sense, we are talking about technology CAD, technology computer aided design. So initially the CAD is not for electrical engineering. CAD is, for example, this kind of thing is a traditional CAD. If you have certain mechanical structure or buildings, airplane, then they have complicated shapes. So using the computer, so they design these complicated components or parts. That was original meaning of CAD. However, we are introducing the prefix technology, and here technology means that semiconductor device technology. So simply speaking, the TCAD means that the activities to use computer simulation to develop our semiconductor device technology. So this is the one. Of course, you may say that technology is so general terminology. How can we say that semiconductor device technology as technology? So yes, you are right. So this is not very specific name, but anyhow, everybody in this field is using the term ticket. So we will just follow the convention, naming convention. Okay, so then let's go to next one. Then how about the ticket? Ticket is actually sold. I mean that there are companies offering ticket tools. Ticket tools, once again, is actually ticket means a collection of different computer programs like process simulator and device simulator and other simulators. The collection of these computer programs are called as a TCAD suite. So some companies sell their own TCAD tools with a very high cost, high price, and the most dominant one is of course Synopsys and other companies like Silvaco or GTS. There are many companies, and Synopsys, for example, Synopsys is not just a ticket company. This is a kind of a giant in EDA, not only in this ticket field, but more wider field like called as EDA, electronic design automation. But anyway, there are small companies, relatively small companies, Silvaco, GTS, and Coventus. They are more specialized to the process emulation. And Taiwanese company Cogenda, and these companies are for optoelectronics. And also we have other companies operated by RAM. research, such kind of companies. Nowadays, nowadays equipment developers are also operating their own ticket companies because nowadays fabrication becomes really difficult. So this is um, companies. So simply speaking, I wanted to use ticket programs. The best way is just to ask your professor. Then he or she will buy those programs for you. Then it costs quite a lot, but it's none of your business. So you will have programs, then you can use it. That is quite a simple one. However, in this lecture, in this course, we are not doing such kind of a fast way. In this course, you will build your own code. So sometimes people say that you don't have to reinvent the wheel. But however, in this course, we intentionally reinvent the wheel or just to fabricate our own wheel once again. For what? By doing this one, by doing this kind of exercise, you will understand what is important in this field and you will fully understand the internal procedure behind your ticket tool. Then you have some analytic capabilities to understand the result of your ticketed result. Okay, so now let's go to more detail about ticket. This figure shows the involvement of ticket tools in the real new technology development. So now let's say that nowadays, for example, a certain company has successfully made a 3 nanometer node, then next target will be, for example, 2 nanometer node. Then what will happen? So this is the typical way they develop the next generation technology. For example, okay, 3 nanometer node, we have introduced, for example, gate-all-around transistor. And for 2 nanometer node, we will just keep this kind of architecture and just a little bit shrink our structures. Okay, then they eventually wanted to make their device fabrication. However, device fabrication is not available at the initial stage of your technology development. You have no 2 nanometer node right now. Then what you have to do is first just to imagine the size of your next generation technology and using this process simulation in computer. So you just make candidate for your next generation structure. Then this resultant device structure is handed over to the device simulator, and this device simulator, based upon the device structure, it can predict the electrical performance. Electrical performance means that when you apply certain voltage, then it will conduct how much ampere in this device. That is electrical performance of our transistor. Then if we stop here, then there is no improvement. However, based upon this this prediction, then we think that how can we obtain better performance from this technology? Then what we can do is now we slightly change the device parameters. Then we will have slightly different structures and slightly different electrical performance. Is it better or worse? Depending on that answer, then we can iterate this process simulation, device simulation, and analysis. This kind of thing can be done repeatedly at the initial state of our technology development when we have no device fabrication. However, now when fab is ready for massive manufacturing, then things becomes a little bit different. Then now we can have silicon data, and when we have silicon data, then we can make a comparison between predicted performance and measured performance, and also our device simulator or process simulator can be calibrated to the realistic silicon data. Then now the loop becomes more complete, and these loops are run forever until we have the well developed technology. So this is quite a routine procedure in our technology development. So companies have some of few development teams, not only for next generation or second next generation. They have multiple teams assigned to each technology node, and they are doing those kind of things. So as I explained you already here, there are two important steps in this TCAD simulation. One is process simulation. So just to try to build certain kind of structure, and device simulation that is related to the prediction of electrical performance. So since our goal is eventually build an electrical system, so this one is directly related to its final goal. However, process simulation is related with manufacturability. If this structure cannot be made, or even when we make it, there are too much variation inside it, then we cannot adopt those kind of process steps. So that is uh, assessed by our process simulation. So let's go to the next slide. And we have various TCAD tools. Yes, as I told you before, if you buy a TCAD license, then you will have many different tools. Tools means that here computer programs, and usually what we can get from TCAD tools or TCAD framework is like this. It provides process simulator. Okay, using this process simulator, you can simulate the fabrication process, and here you have a little bit different one, a similar one, process emulator. Process simulation and process emulation, their difference are like this. Simulation means that they really try to follow certain physical rules. So they follow, for example, some diffusion rule of dopants inside the semiconductor. Emulation is not trying to follow exactly the physical rule, just to emulate and make a seemingly possible device structures. But anyway, they are quite closely related, and using these two tools, we can generate certain um, device structures. And another way to generate the structure is structure editing. This is just like a drawing your device, and yes, that is quite an easy way. However, this is nothing related with realistic process. So this is usually used at the initial state of our technology development. At the initial stage, we have no silicon data. Then just to make our expectation about final structure, then we can easily construct this kind of thing using structure editor. Once we have anyhow generated device structure, then we can simulate its electrical performance. And usually this device simulator gives us some information about physical quantities inside the semiconductor structures. So usually this information is 3D volumetric data. So we have to visualize this three-dimensional data. Then we have to have a visualizer for this kind of data. This is a traditional scope of our ticket framework. But nowadays, I want to say that nowadays we have more wider definition about ticket. For example, atomistic modeling. Atomistic modeling is especially important for process simulation. For example, if you deposit certain kind of a layer into your semiconductor, or if you do such kind of etching process, for example, nowadays, in order to fabricate a certain kind of devices, usually you have to etch your silicon quite deep. I mean that. So although this is quite short or narrow, however, you have to have a very tall etched profile. So when we have such kind of deep etch, then how can we simulate this kind of a process? Then it is always related with what? Related with surface reaction at this point. So here we have etchant, and here we have substrate, and etchant and substrate atoms are interacting and they are etched, and when time elapses they become etched. So here we have to model the surface reaction, and this kind of surface reaction is well modeled only by atomic scale modeling. So nowadays it becomes more and more important in this one. And another part is compact modeling. Compact modeling is not actually within the traditional TCAD tools, but nowadays TCAD is now expanding its scope, and now it becomes more evolving, more generalized terms called the TCO. D means that design, T is technology, and CO means that co-optimization. Now, um, the guys in fab or device engineers not only considering only technology, but at the same time also consider this design. So eventually they wanted to provide better logical blocks to their customers. So not only this framework, TCAD framework, but combined with these compact models, they just wanted to a larger system to optimize their logical subblocks. So we have many tools, but I think that due to the time limitation, maybe in this semester we will briefly touch only process simulation, process emulation, and device simulation. I'm very much interested with the compact model also. However, I'm afraid that we cannot talk about compact model in this semester. Okay. So then now let's go to the process simulation. Um, Process simulation, we have three-dimensional device structure. You know, in this figure, we are now looking at three-dimensional planar MOSFET. Planar MOSFET is a somewhat old technology. You know, introduction of FinFET, the first generation of three-dimensional, really three-dimensional multi-gate MOSFET, was more than 10 years ago. So this planar MOSFET is a somewhat old one. However, even in this old technology, the structure is not that much trivial. Okay, so you can easily understand. Here we have a certain contact, here we have another contact, and also we have another contact, And here we have another contact. We have four contacts in these devices, and in between there are many different structures. For example, here we have extremely narrow gate oxide, and here we have also spacers. So this kind of thing is non-trivial, and but this is just planar MOSFET. Compared to the state-of-the-art transistors, it is much simpler. Anyway, the structure of our transistor is so complicated. It is complicated because we have, first of all, we have several materials. Silicon or silicon germanium alloys. Those kind of materials are used in the channel materials nowadays, and we are planning to adopt other materials like pure germanium channel or 3-5 or even two-dimensional materials into our channel material. And also we have insulating materials like oxide, nitride, hafnium oxide. We have many different insulating layer, and although I have not shown it here, we have also metals. Many different metals are involved in this scene. Also, we have position dependent doping profiles. Doping profiles here, colors means that the values of, okay, so I'm sorry about that. So let's just go back. Position dependent doping profiles. Some part is n-type dot and some part is p-type dot, and depending on their doping profile, their electrical performance is heavily affected. And another one is, here we have unstructured mesh. Here unstructured mesh means that, let's consider certain cube. We have a very simple cube, and this is a three-dimensional quantity. Then how can we represent this cube in our computer simulation? Typically, when you say that structured mesh, then we use this cube or cuboid as a basic building block of our mesh. However, unstructured mesh means that we are now using tetrahedral as a basic building block of our mesh description. Okay, so then this cuboid is divided into several tetrahedral, so then we can express many different shapes using those tetrahedral. Okay, so three-dimensional device structure is quite complicated, as you can easily expect. Also, another complication is process is not a universal process steps. We have many different process steps to achieve the final goal, like building a transistor. For example, here I have just prepared many different steps required to build a transistor. Then in this course, wafer preparation is not covered. So although that is important one, usually the companies just buy wafers from wafer companies, so we are not interested with this one. However, oxidation is of most interest in our process simulation, and photolithography. Photolithography is so important, so therefore instead of being a part of TCAD, it has different independent research field called as OPC, optical proximity correction. So when we draw this kind of layout, then it can be transferred to the silicon in a given way or not. That is discussed by this OPC tools. So although that is so important, but this is a huge part, so I will not talk about this OPC because OPC is a completely different part. And etching is a part of our course and also part of TCAD process simulation. Etching is nowadays so important, really important. Think about your NAND. When you buy a USB driver, then you have a NAND in it, or your SSD also you have many NANDs. Then nowadays these NANDs are all 3D NANDs, and these 3D NANDs requires once again very deep etched profile. So etching is so important, and since that is so deep, and we have to control our etching process quite accurately, so etching is quite important in our TCAD simulation. And deposition, yes, deposition is just to introduce a new material layer on top of a predefined material layer. So deposition is quite important, of course, and oxidation and deposition are a little bit different. Oxidation means that silicon was there and introduce a certain material, then convert our silicon into silicon dioxide. This is oxidation. And deposition means that here we have a silicon and here we introduce different materials or new materials on it. So silicon is not consumed by this kind of deposition. And ion implantation is related to the doping. So there are two major ways to introduce doping. One is diffusion and one is ion implantation. However, nowadays the processes are so much scaled, so ion implantation is the major way to introduce impurities into our system. So these are major steps we will talk about in this lecture. Of course, we have other ones like making on interconnect lines. However, although it is important, but that is not covered in this course. And EDS, yes, this is preventing the electrical discharge, but it's not also covered in this one. And packaging, nowadays you have much heard about packaging is the most important nowadays, because yes, they wanted to introduce multiple functionality into one chip, and this is the best way we can do. However, usually these steps are regarded as back end of line. So back end of line is not covered in this one, although nowadays its importance is becoming more and more improving. Okay, so now let's go to our discussion about device simulation. I think that I have only one slide for this one. The major difference between process and device simulation is, in the case of process simulation, we cannot identify one single rule for our process simulation. For example, oxidation has its own physical rule. Etching has different physical laws, and deposition, ion implantation, they are all different physical properties for physical behavior. However, in the case of device simulation, the basic principle is quite simple. Whether electrons are moving or not, whether holes are moving or not. That is just the only way or the only thing we have to consider. So this is related with the movement of our electrical carriers. So simply speaking, device simulation is a kind of a transport simulation. Electrons transport, holes transport. Once we can simulate these transport accurately, then that's all. So since transport theory is well established, we can just follow the hierarchy of these hierarchy of this theory, and in this theory the quantum transport is on top of it, so most fundamental. However, it requires most heavy computational burden, and Boltzmann transport equation we can little bit reduce the computational burden. However, this is far much more complicated than the most efficient one called drift diffusion. So in reality, when you say the TCAD device simulation, this is more or less almost exclusively representing the drift diffusion model. So in this semester, I think that we will concentrate on this drift diffusion model. The physical accuracy of this drift diffusion model is not that high compared with this higher advanced models like the Boltzmann transport model and quantum transport model. But unfortunately, these models are too much complicated and it takes quite a long time to get a result. So instead of doing these kind of advanced simulation every day, people are just to introduce many calibrating parameters. So by introducing those calibrating parameters, then anyhow the result of a drift diffusion model is matched to, for example, advanced quantum transport simulation result, or even measured IV characteristics. Then once that is calibrated, then this calibrated drift diffusion model can be used for practical purpose. Usually the time requirement is like this. Overnight. It means that once you have a certain problem, then your engineer can learn it overnight, and when he or she come back to the office, then the simulation result should be available to them. Then they can do some research work or some analysis, and before leaving their office once again, they can start their long simulation, overnight simulation. So however, these quantum transport simulation or BT simulation usually takes days, sometimes weeks. So this is far beyond than acceptable time scale. So we will concentrate on this drift diffusion model. And from this drift diffusion model, we can also make the models used for SPICE. So you know, SPICE is the tool to simulate the electrical circuit, not the electrical semiconductor devices. However, compact model is a little bit different story, so we will concentrate on this drift diffusion model in this semester. If you are interested, I can recommend you many valuable references. Okay, so I think that that's all for our introductory lecture 1, and you have your first homework. So due is this Wednesday, so just before our lecture start, please submit your simple code to our GIST LMS system. The program is just to print hello world and just to submit your report. Your report can be quite short. So this is quite a simple program, so you don't have to explain every detail of your program. But we have two purposes. One is at least you have to start the programming in your own environment. So I have no specific requirement on your development environment. For example, you can use MATLAB, you can use Python, and also you can use C, C++, Fortran, whatever. Is it because I will not much interested with your own implementation. I will not check your implementation in detail. Important one is once after this semester is over, then you have to have your well-developed in-house device program and process program for suitable for your own purpose. Okay, so therefore don't be so much concerned about program or development environment. But anyhow, since this course is related with numerical analysis, at least later on you should be able to do certain mathematical functions like this. This is matrix, vector, and vector, and A and B are given, and you wanted to calculate a vector x. You should be able to do this. But fortunately, all of these languages have sufficient support for this kind of one, built-in support, or through well-developed libraries, you can easily do this kind of things quite well. So don't be worried about that one. So are you with me? In homework 1, you can just write a short code and submit it. Then that's all for our lecture 1. Okay, so we have 5 minutes left, but if you have any question, then please let me know.
그 밴드게이트 설명하실 때
오케이.
앞에서 거의 뺀 이해 같은데 그 언제 영어로 바뀌고 일로 바뀌는지 그 원리가 잘 이해가 안 되세요. 그러니까 AB를 닫으면은, 그러니까 게이트를 닫으면은 커넥션이 돼서 저기 아웃 쪽에 1이 그러니까 어떻게 되는 건가요? 그러니까 AB를 게이트를 닫으면
Okay, so I cannot delete it any further. Okay, so here you must do some self-study on this one, but I want to summarize. Here you have 4 different devices, 4 different symbols. Yes, can you see it here? And although they look quite similar, they have some differences. So the lower 2 devices has no bubble in it, and here we have bubbles. Yes, so these bubbles just represent that the one with bubble and the one without bubble behave differently. This one without bubble is conductive when A is 1. In this case, it becomes conductive. And in this case, when A equal to 0, then it becomes conductive. Then how can you generate such kind of 2 different devices? This is also the art of our device fabrication and using the N MOSFET we can realize this kind of behavior also when we introduce P MOSFET. Then we can achieve this kind of behavior. So please do your self-study about N MOSFET and P MOSFET. They have different polarities, and following their different working principle, they can achieve this kind of behavior. Okay. Any further question? Okay, so if you don't have a question, then right now our LMS system does not have homework submission for homework 1, so I will open the homework 1 submission after this session is over. Then since it is not that difficult, you can do it within time without much difficulties. Okay, so then see you Wednesday, and yes, that's all.